Okay, hi guys, we've got ourselves a physics question here, and the question says that a particle of charge Q is constrained to move along a line between two other equal charges of Q fixed at x equals plus or minus a. What is the period of small oscillation? You can see I've underlined this statement here. So we have to determine the period of small oscillation. So very small displacement. So what is going to be the period of that motion? So that is what we are interested in. So let's quickly look at the setup. Okay. So since we have the motion along the x-axis, so let's have our horizontal line. You see this is our horizontal line. And they said a particle of charge Q is constrained to move along this line between two other equal charges fixed at these 2 points. So let's say we have the extreme point here to be minus a and the extreme point here to be a. Okay, so we have that this can be the origin. Let's say this is the origin of the motion. So we have this. If a charge is placed here, Q, and the other charge is placed here, and we want to place this charge Q, because they said they have equal magnitude, that is why they are QQ. So let's want to place this guy at the middle. I'm just assuming you can place it anywhere if you like. But if you place this guy here at the middle, let's just say we are placing him at the middle, then you expect, let me just put it here at first, I'm still going to do something to it. So we expect that there will be a repulsive force between these two charges. That is, this charge will repel this charge according to law of electrostatics that says that like charges repel and unlike charges attract. So this charge we want to repel it, and there's a force at which it is using to repel it, and that is the Coulomb force. Likewise, this charge too, we want to repel this charge. So that means this guy here, this charge here, will first move along this line. Then at one point it is going to move along, we first move along this line due to this charge. Then at one point it's going to move along this line due to this charge. And this will continue to happen. This guy will keep moving to and fro, and that gives us something that we know in physics, and that is simple harmonic motion. So this motion, this charge is going to exhibit, as a result of these two charges, is going to be simple harmonic in nature. So we know that for simple harmonic motion is a type of motion that goes in a to and fro manner, and the acceleration is usually proportional to the displacement from the fixed point. You know all those. I want to assume we know that. Okay, so we can actually do something. So let's assume when the charge was placed initially here, then it's moved to this point at first. It just got displaced, small oscillation. There's small displacement. So the charge is here. Let's say from here to here, the displacement is x. Okay, just when it is placed there, due to we know it's going to be displaced at first. I'm just assuming it first moved to this direction. Okay, so from here we can have the distance from this charge to this charge. The distance from this charge to this charge is going to be, from here to here is a. Don't mind this minus. This negative sign just tells you that it's at the negative part of the x-axis, just the direction where the distance is. But the magnitude of this distance is a. So that means we expect from here to here to be a minus x. Likewise, from this charge to this charge, we expect the distance to be, this one is a and this one is x. That will be x plus a, or a plus x, and now you want to put it. Okay, so let's add this charge. Let me bring this charge out. So let's say I have this charge here. If I have this charge here, the force exerted upon this charge due to this charging is going to be repulsive. So the force, I expect the force to be acting in this direction. Let's call it F1. The direction of the force is that way. We have already indicated. Okay. And for this other charge, the force exerted upon this charge here is going to be in this direction, and that is F2. So let's say this is F2. Okay, sorry, let's just put it this way. Okay, so this is moving to the east, this is moving to the west. So we can find the resultant force on this charge. So we know that, okay, let's first find this magnitude. We know F1 is going to be this. As the according to Coulomb's law says that the product of the force of attraction or repulsion between two charges is proportional to the product of the two charges and inversely proportional to the square of the distance between them. So we know that the two charges are this. So F1 is going to be K, there is a constant, this is a constant, KQ squared, that's Q times QQ squared divided by A minus X all squared. And we are going to have our F2 to be KQ squared divided by X plus A squared. So where our K is actually, write it here. So where K is a constant 1 over 4 pi epsilon naught. We know this permittivity of free space, and this is approximately 9.0 times 10 to the power of 9. I guess Newton meter squared per coulomb squared. So this is our K. So you can just add this at the back of our mind, but we don't need to. Don't let us substitute for K yet. Let's just solve. Okay. So the net force, let's call this Fn, the net force on this guy, on this charge, is going to be the difference between these two forces. So that's because one is going east and the other is going west. Okay. Either way, moving in the same direction, we just add it. So now that we have this, we can substitute for F1 and F2, and that gives us KQ squared over A minus X squared, then minus KQ squared over X plus A squared. Okay, so now that we have this, we can play around this guy. It's actually A minus X squared. I can interchange this since addition is commutative, so I can say this is A plus X squared. It doesn't matter, it's the same thing. X plus A is the same thing as A plus X. Okay, so finally the LCM, I'm going to have KQ squared divided by, let's say, A plus X squared, times A plus X squared minus KQ squared in brackets A minus X squared. Okay, and this guy here gives you, let's factorize KQ squared out, and this gives you A plus X squared. Let's have this A plus X squared minus A minus X squared divided by, this is difference of 2 squared down here, so I can write this as A squared minus X squared all squared. So I've not done anything special. If I expand this, this is still the same thing as this. So this guy gives me KQ squared, open bracket. If we do this one, okay, let's open this up. This is actually A squared plus 2AX plus X squared. And that will be minus, open bracket, this is A squared minus 2AX plus X squared divided by, this is A squared minus X squared all squared. So we have this. Okay, so if we play with this A squared, we cancel this A squared. 2x we cancel, X squared we cancel X squared. 2x plus 2x is 4x. So this will give us KQ squared dot 4ax divided by A squared minus X squared all squared. Okay, so let me get rid of this. Okay, so the question says for small oscillation, and we have our net force to be this. So for small oscillation means that x is very, very small. That is, for small oscillation, we have that x is very small, that is much more smaller than a. Very small, that's the meaning of this symbol, much more smaller than a. So this implies that if I even square this guy here, I expect it to be very small again. That is, if let's assume x is maybe 0.1, it is smaller than, let's say, a 10. right? So if we square this is going to be like 0.01. You can see that it's going to be smaller than 100. So that is what this simply means. So we can then continue from this, and okay, since x is very small, so let's neglect, so neglecting the value of x, or let's just say neglecting x. So we are going to have that this guy, the net force Fn, is now going to be kq squared dot 4ax divided by a squared all squared, and a squared all squared is same thing as a squared raised to the power of 4. So what we've done here is that, let me explain again. We assume that x is too small, so it's like approximately 0, so that's a squared, but it's going to have a value here because we don't want this expression to vanish. You cannot say, okay, this x2, because you neglected x at the denominator. Okay, let's say neglecting x squared term. Maybe that will make it, that will make sense that way. Okay, so this x, we still want a value, you understand? So that is why we cannot neglect the term here. But x is very small, so squaring it will give us a smaller value. So that is why we neglected the x squared term at the denominator. Okay, so if this is 0, this gives us a squared minus 0. That's a squared raised to power 2, and that's a raised to power 4. So 1a cancels 1a. So we have, eventually this guy will be 4 kq squared x divided by a cube. So our net force for small oscillation is actually 4k q squared x divided by a cube. Okay, so moving on, since we have our net force to be this, so recall that F is equals to ma. So since F is ma from Newton's second law of motion, and we can say, though this a is acceleration, so let's not confuse it with this. So let's call it mx dot dot. Don't forget, if you find the time derivative of displacement twice, you get the acceleration. So dot means dx dt, dot dot means d squared x dt squared. So I can replace this guy for this net force, the same thing as, so this guy can be written as mx dot dot, that's the force here, is mx dot dot, is equals to 4k q squared x divided by a cube. Okay, so our acceleration x dot dot is now 4k q squared x divided by a cube. So this is our acceleration. Yeah, okay, let me write this well. This is our acceleration for the motion. Okay, we're almost done. Okay, so let me get rid of this. Okay, so since the charge is performing oscillation, so since the charge Q is performing oscillation, so we can compare this equation with the acceleration for a body performing simple harmonic motion. So recall that for a body performing oscillation, acceleration x dot dot is given by minus omega squared x. So it's given by minus omega squared x, where omega is the angular speed of that body. Okay, so since we know this, let's call this guy equation 1, and let's call this guy equation 2. So comparing equation 1 and 2. So we compare equation 1 and 2, meaning that all the term here, the terms we have at this point here, is actually our omega squared. You'll be like, what about the negative sign? Negative sign doesn't mean, it only implies that the acceleration is usually opposite to the displacement. That is, it moves in opposite direction to the displacement. Body moves in opposite direction to the displacement. Okay, so that is what we mean by that. So we can compare equation 1 and 2. So omega squared is actually 4k q squared divided by ma cubed. So that is our omega squared, which is angular speed, and omega is actually square root of 4k q squared divided by ma cubed. And we know that this omega guy, recall that omega is actually 2 pi divided by period. We know this from simple harmonic motion. Let's use the period. And so this guy is going to be equals to this 4k q squared over ma cubed. Okay, I'm going to get rid of this equation down here. So if you make t the subject of the formula, period t will then be, just take the inverse of both sides, 2 pi, and that's going to be 2 pi roots ma cube divided by 4kq squared. So this is our period of oscillation, period of small oscillation for the charge. This is period of small oscillation. Okay, so guys, if you find this video helpful, kindly hit the like button and put a comments in the comment section, and don't forget to subscribe to my YouTube channel. See you guys soon. Thank you.